KICP Colloquium. Today we're happy to have back with us Colin Bischoff. Started out at Stanford as an undergraduate, came here for graduate school working with Bruce Weinstein on Quiet, I believe. Graduated in 2010, went to CFA and worked on some combination of BICEP 2 and Keck and the larger BICEP Keck collaboration. Working on instrumentation, foreground modeling, B-modes, all that good stuff. He's now faculty at University of Cincinnati and continues to play a big role in the BICEP Keck collaboration, also working on CMBS4 projections and thinking about future experiments. So with that, I'll turn it over to Colin.
Thanks, Eric, and can everybody hear okay? It's fun. Okay, great. Yeah, so thanks for having me. I thought I just turned it on.
Oh, it's not.
I think it's just, yeah.
I'm down.
Thanks. Okay?
Yeah.
All right. Yeah, so thanks for having me. It's always nice to be back in Hyde Park, especially because everything keeps changing every time I come here. So it's yeah, anyway, great visit. So I'm going to be talking about new results from BICEP and Keck. So we had a paper with our latest B-mode results that we got on the archive last month, and I think it's showed up on the PRL website in the past week or so. So hopefully you've seen it. This is the first time I've talked about these new results. I tried to keep it short and succinct, and suddenly, as of like 15 minutes ago, I'm worried that it's too short. But you should all feel free to ask any questions or anything like that at any point. So don't be afraid to interrupt me. I also finally updated the photo on my title slide. It had always been a very BICEP 2 centric title slide, an old picture of BICEP 2 with some nice B-modes in the corner. But really our data, we're getting more and more data from Keck, and that's really contributing to our result a lot. So I figured we should have a Keck photo, and this one's pretty great. This is our winner over Robert. He's now in his 12th winter at the South Pole. Well, he just finished it. I guess he's in warmer climates now. All-time record holder. So this is the Mr. South Pole, Robert Schwartz, right here. Photograph taken from our calibration mask, which supposedly took him quite a bit of effort to get this lined up just right. So, but I really appreciate these results. So there's a nice photo of the Keck array with all 5 telescopes, and Robert in the South Pole sunset. All right. So given the audience here in Chicago, I'm not going to spend a whole lot of time on the science background because I think there's a lot of real experts in the audience here. But just sort of obligated to show one of these timeline of the universe images, right? So here's a very conceptual sketch of our universe going all the way back to the Big Bang. And I'm, of course, what we study is the cosmic microwave background. So this is light that was first released, first decoupled from matter, a time about 300,000 years, 400,000 years after the Big Bang, when the temperature cooled off enough for the universe to become neutral. So the universe is transparent to allow us to look back to that time, but what we're really trying to understand with BICEP and Keck is we're trying to learn more about what happened at the very earliest times, at the time of the Big Bang. And so to do that, we look at signals that are embedded in this microwave background. And so if something like inflation occurred in the early universe, it would produce both density waves and gravitational waves that propagate, persist through time, and leave an imprint on the microwave background. So what we are trying to do is we're trying to look at the signals of these perturbations at this time, about 400,000 years after the Big Bang, to infer something about inflation. And in particular, what we're searching for is these gravitational waves, which are frequently referred to as the smoking gun of inflation. So some sign that the universe underwent a very rapid and exponential expansion. So we're doing that by measuring polarization of the microwave background, and in particular, measuring this B-mode polarization. So the idea here is that if we have both these density waves and gravitational waves, that the density waves are only able to produce E-mode polarization by their symmetry, and yet the gravitational waves will produce both E-mode and B-mode polarization. So the distinction here is that this E-mode pattern is something where if you have a fluctuation along the horizontal axis, the pattern here is oriented both parallel and perpendicular to that direction of fluctuation, whereas for the B-mode, it's oriented at 45 degrees. And so in the case of the density wave, you only really have one direction associated with this oscillation. It's the wave vector of this density wave. And so you can the only directions that are relevant are either going to be the directions parallel or perpendicular. You don't have a symmetry breaking to select between these plus and minus 45-degree angles. Yet with a gravitational wave, you're going to have an additional direction involved, which is going to be the polarization of the gravitational wave. And that allows you to break that symmetry and produce a B-mode type pattern, which we can then search for. So I'm going to talk a lot about this tensor to scalar ratio R. Essentially, we're at the point where we're trying to measure just one parameter. We're trying to measure whether this sort of signal is present and if we can get an amplitude on it. So that then brings us, again, I realize I'm moving very rapidly here, but hopefully a lot of this is familiar to everybody. So this brings us to the CMB power spectra. So we have angular scale in terms of the spherical harmonic multiple here on the x-axis, and fluctuation power on the y-axis, covering a wide range, many orders of magnitude, going from the temperature fluctuations all the way up here to the E-mode polarization, which has been detected and fairly well characterized at this point, and then down to B-modes, which is what we're ultimately trying to detect. So shown here in this figure, we have both B-modes from the gravitational lensing and E-modes, which I'm not really going to talk much about at all, but which are both a really interesting scientific target, and also are ultimately for measuring this gravitational wave signal are eventually going to be a problem that we have to deal with, actually quite soon are going to be a problem that we have to deal with. But I'm going to focus instead on this gray band, which is showing kind of a range of estimates for that gravitational wave signal with this tensor to scalar ratio ranging from 0.1, which is already getting ruled out at the current sensitivity of data, down to 10 to the minus 3, which is where we hope to be in, well, not really that many years now. So the experimental design of BICEP and Keck, the experimental strategy, is to focus here on this area where this gravitational wave, this tensor signal is peaking. This corresponds to multipoles around L of 80, which is a few degrees in terms of angular scale. And so by targeting this area and going very, very deep in a small region of the sky, that leads to an experimental design where you don't need high angular resolution. You're talking about a signal at fairly large angular scales. What you do need, as you can see from kind of the number of orders of magnitude on this y-axis, is you do need a large amount of instrumental sensitivity. So the other issue, if you're trying to go after the signal, which is what a fair bit of this talk is going to be about, is you have to deal with galactic foregrounds. So these are, so this is a series of maps from Planck, polarization maps in Stokes Q and U, ranging from 30 gigahertz at low frequencies up to 353 gigahertz at high frequencies. These are full sky maps. In galactic coordinates, you can see the galactic plane here. And this kind of highlights the challenge we face in just getting at the CMB at very, if you're trying to get to very sensitive measurements of the CMB. So what you can see here at low frequencies is you can see the galaxy showing up brightly in the synchrotron foreground. So this is free electrons that are spiraling in the galactic magnetic field, emitting microwave radiation. And then if you go all the way up to these high frequencies, you can see the map start to become dominated by thermal emission from dust. And so clearly at the very low frequencies and the very high frequencies, these things are very bright. Obviously, it's also very bright in the galactic plane. But you might convince yourself that, okay, if you go to these intermediate frequencies, you go far from the galactic plane, that you can find a nice clean region to study. But it turns out that for the sensitivities that we're trying to get to, there essentially is no clean region. There is no frequency where you can minimize the foregrounds to the point of just avoiding them, right? So no matter what you do, and this is, I've highlighted here the area of the sky roughly where we are searching with BICEP and Keck, and at frequencies, where we operate. This BICEP 2 started out at 150 gigahertz, so it's doing something like that little, not quite rectangle right there. Yet even focusing in that area and at these intermediate frequencies, you're going to need to take active measures to handle these foregrounds. Okay, so here's then the program that's been running for the past 9 years now to try to address this problem. So we started off with BICEP 2 that ran for 3 years from 2010 to 2012. This was a single small aperture telescope. Had a focal plane that looked like this, which consisted of 4 tiles with dual polarization pixels, a total of 256 pixels with 512 transition-net sensor kilometers, all operating at 140 gigahertz. And so the projected beam pattern is shown on the sky here in green for 150 gigahertz. So this operated for 3 years, made deep maps, and was ultimately able to detect a beam mode signal at degree scales that we now know is from the dust. So those foregrounds that we saw on the last slide. So this was then followed up by Keck array, and here's this picture of Robert again. And so the idea behind Keck array was to take the BICEP 2 telescope and replicate it 5 times, hence the 5 telescopes that you can sort of make out in this image. And now the really powerful thing about Keck array is because you have this modular system consisting of 5 independent telescopes, we've been able to change out the observing frequency of these telescopes, one at a time over the years since 2012 when this thing was first operating. So it ran for a couple years at 150 gigahertz and was produced data that was quite consistent with BICEP 2 and saw the same dust signal. Now, if you go back and we're looking at these maps again, what we can see is that these foreground signals are, their amplitude is changing significantly with observing frequency. So if you're now able to make measurements not just at 150 gigahertz, but also down at 100 gigahertz, and maybe at higher frequencies as well, you can, for a given signal that you see, you can analyze how its amplitude is changing in frequency, identify it either as a foreground type signal, a dust signal that's getting bright at high frequencies, maybe a synchrotron signal that's getting bright at low frequencies, or a CMB signal that will have, at least at these units, an amplitude that's frequency independent. So with Keck array, with these 5 telescopes, we were able to modify the observing frequency distribution of the telescopes over the years to build up sensitivity at frequencies other than 150 gigahertz, that was the BICEP 2 frequency, So at least in this schematic, what's shown is Keck array observing in 3 colors at 95 gigahertz, at 150 gigahertz in green, and then with 2 out of the 5 telescopes observing at 220 gigahertz at the higher frequencies. And so this is the Keck array configuration that was operating in 2015, which is the most recent data that I'm going to be talking about this stuff. Next, we have a couple telescopes that we have not yet published data for, but BICEP 3, shown here, was installed in 2015 in the mount that once held BICEP 2. This is a larger aperture telescope. It has a larger focal plane, which you can see here. Just for comparison, these detector tiles are the same size as these ones. So you go from a focal plane of 4 tiles to a focal plane of 20 tiles, and it's observing at 95 gigahertz, shown in red, the low frequency. And at the end of the talk, I'll say a few things about BICEP array, which is the plan for the future. Coming in just a year, it should be the deployment about a year from now of at least the first 2 telescopes at BICEP array. The idea behind this is going to be to replicate a BICEP 3 style telescope in much the same way that Keck was a multiple of the BICEP 2 telescope. And so this is still building on this same program of small aperture telescopes at the South Pole. Very high throughput, a lot of detectors at high sensitivity, and extremely good control of systematic errors to make these deep measurements. Okay, here is the collaboration, or at least a good part of it, from a meeting about a year ago at University of Minnesota. So just to give an idea of who's involved here and what the size of the collaboration are, including the PIs of the project, John Kovac, Clem Bright, Jamie Bach, Shaolin Kuo, and a few University of Cincinnati participants, so grad student Steve Palladino, Hunter Fremen Zinkhorn, and Katerina Milta, who's a postdoc in Cincinnati. Okay, so I mentioned the multi-frequency composition of Keck array. So this is a really crucial part of the observing program. And so one of the things that we're able to do is we're able to reproduce a very similar telescope, and in fact reuse the same telescopes, but with detectors operating at a different observing frequency. So these are these detector tiles. They're all fitting into the same Keck array focal planes. And yet they're observing at 95, 150, and 220 gigahertz. If you look, here's a zoom in on the pixels, which are in fact, most of this square area is dominated by an array of antennas that's meant to couple the microwaves onto the detectors. The pixels are significantly bigger at 95 gigahertz because the wavelengths are getting bigger, and hence there's fewer pixels per tile at 95 gigahertz. At 220 gigahertz, we actually don't get any more pixels, and that's purely a design choice in order to reuse the same readout. We just didn't have the ability in the same telescope to read out more pixels without large engineering changes. So in fact, the 220 gigahertz does have a little bit of dead area in the focal plane because the pixels get smaller, but we don't cram any more of them in there. You can see then, these are bandpass measurements made with the Fourier transform spectrometer, and it's showing, as a function of electromagnetic frequency, where the 95 gigahertz, 150 gigahertz, and 220 gigahertz pixels pick up signals, with this black line showing the atmospheric transmission for South Pole or something like it. So you can see that we're using these 3 atmospheric windows that are available. Yeah.
What's the size of those squares at the top?
The tiles?
Yeah.
So the tiles are about a big. So we're actually, for BICEP array, so it's not shown here, but BICEP array is not just, it's not going to be quite the same focal plane as BICEP 3. So BICEP 3 is 20 tiles that are the same size as Keck tiles. BICEP array, we're actually going to a larger tile, so it's going from a 4-inch fab process to a 6-inch fab process. And so the BICEP array focal plane will be a similar focal plane area, but with only 12 tiles instead of 20. The kind of modular design of these will be similar for BICEP array. So this is, rather than Keck, where there's this, the tiles are mounted on this circuit board with readout stuff here. For BICEP 3, the circuit boards are behind the tiles, and that design is still going to be the case for BICEP array. The approach modified with bigger tiles. Okay, so this is kind of repeating maybe what I said earlier, but in a more systematic way. So this is this kind of schematic view of the way the Keck array evolved over time. So it operated for its first 2 seasons, observing exclusively at 150 gigahertz. And of course, if you look at the dates, you can see that the BICEP 2, that first result where it came out, and we saw signals, and then figured out that they were foreground signals not long after. That was 2014, right? So it was all through 2012 and 2013. It's a lot of 150 gigahertz observing, also in part, the kind of R&D cycle of when we were going to have the other frequencies available. So for 2014, what was done was we took 2 of these telescopes at 150 gigahertz and changed them to 95 gigahertz. So we're now exploring lower frequencies, which, in fact, if you're worried about a dust foreground, these actually become channels where it's you're more directly measuring CMB with less of that dust foreground. And then in 2015, which is the data that's now incorporated into the new result, what we did is we further took 2 of these 150 gigahertz focal planes and converted them to 220 gigahertz. And so now what we're doing with Keck array here is we're targeting the dust itself, right, and trying to measure it at higher signal and noise in order to remove it from our data. So while this is, the most recent publication is just through 2015, there's of course been more work and more data since then. So in 2016, we then took out these 95 gigahertz focal planes, replaced them with 220 gigahertz, and so you can now see that the Keck array is mostly targeting those high frequencies. This coincidentally, well, not coincidentally, it was also BICEP 3 is online and observing at this point, which was a 95 gigahertz focal plane. So that the idea at this point is that BICEP 3 is really working at the low frequencies, with Keck array working at the high frequencies. That also works out well because the larger aperture of BICEP 3 gives it its diffraction limited beams can be smaller at 95 gigahertz, whereas for Keck the beam size at 95 gigahertz was getting fairly large. What we've done in the last 2 years was we took out this last remaining 150 gigahertz focal plane, and we put in something at even higher frequencies at 270 gigahertz. And so this is really this is a question about whether the dust is getting brighter faster than the atmosphere is getting bad. So as you go to higher frequencies, it's more and more difficult to observe from the ground. Yet the dust signal is of course continuing to get brighter. And so the 270 gigahertz, it's the data analysis is still a work in progress, but what we think is that this is in fact going to be even a better channel for measuring dust than at 220 gigahertz. And of course, having more distinct frequencies does also give you it gives you a lever on more complicated foreground models as well. I'll talk a little bit about this soon. Okay, all of these experiments are of course operating from the South Pole. So for many people in the room, this is a familiar or even welcoming, home-like place for you. So this is an aerial view. This photo is obviously from a long time ago because, for instance, SPT is not even there. I'm not totally sure who this was all handed down from, but but probably like most of the photographs from South Pole, it was taken by Robert at some point. So the South Pole Station is, of course, it's at, in fact, the geographic South Pole. There's a marker that is usually somewhere around here that is our, where the actual axis of rotation of the Earth comes up through the glacier. It's a really very, very excellent site for millimeter wave observing. Probably just about the best on Earth you can find. It's at high altitude, 2,800 meters. That's like 9,300 feet elevation. So you get there the first day, and you can really feel it, particularly if you try to run up some stairs. And the atmosphere is extremely stable, as you get from having, essentially no geographic features anywhere within sight other than the horizon. You're sitting on top of a very large glacier, and you only have one day and night per year to drive winds and weather and things like that. The area of the sky that we observe, that small little rectangular region on the sky that I marked out as the BICEP 2 field, is always available overhead. It just rotates around our heads 24 hours a day, and we can stare at it as long as we want. And then the thing that really is the difference maker is, of course, that we can go to this very exotic, very remote site, and yet we're able to operate a complicated physics experiment there with excellent support, with electrical power, with a place to stay, with computers, and astonishingly, the ability to get our data back via satellite links in not quite real time, but maybe a 24-hour delay. So all this stuff together makes this just a really exceptional site to observe. Okay, so most of what I'm going to talk about for the rest of the talk is the new results. So this is, we refer to this as BK15, and so what that means is all BICEP and Keck, all BICEP 2 and Keck data through 2015. I'll put in BICEP 2 because we don't actually put BICEP data into this analysis anymore. That's I guess history at this point. But this is so this is all of BICEP 2, and then it's Keck array for 2012 through 2015. So that's 4 years of Keck array data. So starting out here with the 95 gigahertz maps, so what you're seeing is the CMD temperature fluctuations and the polarization in Q and U. And then on the right-hand side are jackknife maps made from taking our data set, splitting it in half, constructing maps from each half, and differencing them. The signals should difference away, and in fact they do. And what we're left with is just the noise. So you can also think of this as a visualization of the noise level in our map. Or you can read the noise level off on the bottom right of the slide. So this is now a deep 95 gigahertz map, and as a reminder, it has 2 Keck telescopes operating in 2014 at 95 gigahertz, and those same 2 telescopes operating in 2015 at 95 gigahertz. So we would call this 4 receiver years of Keck 95 gigahertz to achieve this map depth here. So what you're seeing in Q and U is you can kind of see a vertical pattern in Q, which again stokes Q is the difference in polarization between vertical and horizontal directions in these coordinates. And in U, you see kind of stripes at 45 degrees. And so this is a visual sign that these maps are dominated by E-mode polarization, because if we're talking about vertical and horizontal polarization, we're seeing fluctuations in the vertical and horizontal directions. So that's E-mode. Okay, so we can then switch to the 150 gigahertz maps, and you again see that E-mode polarization pattern here. The noise level is lower because this, of course, represents more data. This is all of BICEP 2. It's all of Keck for 2012 and 2013, plus some additional Keck data in 2014 and 2015. I believe it adds up to 17 receiver years of Keck. So it's actually, yeah, it's pretty impressive how the data keeps keeps piling up. And of course, you know, you're only increasing this map depth as 1 on the square root of your time, your integration time, but you know, really steady progress has been made over time. And in fact, not just steady progress, but a lot of work has been put into, you know, every year trying to get the last bit of performance out of these telescopes. So we, as I mentioned, we see again this E-mode pattern, and also it's maybe less obvious from E-modes, but if you look at the temperature and you flip between 95 and 150, you know, we're obviously seeing the same CME, which is nice and reassuring. And in fact, you know, that would it's harder to see from maybe the E-modes, but it's certainly there too. You can also see that the angular resolution is better at 150 gigahertz just because of at higher frequencies we have a smaller diffraction than we need. Okay, so the new data, of course, is 220 gigahertz. This is quite a bit noisier. In part, it's because it's just 2 Keck receivers operating for 1 year, but also a lot of that is because the atmosphere is in fact a lot noisier at 220 gigahertz. However, this is, you know, it's going to be worth it because the dust signal is getting brighter there too, right? So if we're really talking about trying to clean out that foreground, what we're interested in is the signal and what that does. And yet, you know, if you look at, say, that the temperature signal is the obvious visual impression, you can see that that's extremely consistent. Noise level, though, is in the map is about a factor of 10 noisier than 150 gigahertz. Okay, so we take these maps, and then the next step is to calculate their angular power spectrum. So shown here is angular power spectra. These are the E-mode spectra. And it's for those 3 BICEP Keck maps that we were just looking at, and I've also included here the Planck 353 gigahertz map. So this is from the Planck satellite, cut down to our field, and in fact also filtered so to observe the same loads as our 150 gigahertz map. But basically, this is Planck measured in our field. And there's a couple, so you can see these angular power spectra. It's the auto spectra down the diagonal, and then cross spectra between various frequencies off diagonal here. And there's a couple, well, there's 3 different models that are plotted here, but the first is just in the black line is just what you would expect from the standard lambda CDM E-modes. That's the microwave background. And then in red, we've added a dust foreground, and the dust model that's shown here in red is actually from the prior analysis. So this is the BICEP Keck 2014 analysis, the previous paper. And in that analysis, we fit a foreground model, and so that foreground model has been added to the lambda CDM E-modes that is shown in red. And so what you can see is that, so again, this is the E-mode spectrum. It's quite a bit larger than the B-modes. You'd expect the foregrounds to be, you know, it's going to be less significantly impacted by those dust foregrounds. And yet what you can see is, okay, at 95 gigahertz and 150 gigahertz, yeah, that impression is quite correct. You know, the foregrounds are not adding significantly compared to the CME E-modes. But at 220 gigahertz, you can see that the foreground is a significant increment over lambda CDM, and for Planck, even in our field, which is an extremely clean field, the Planck E-modes are dominated by the dust foreground. But the other thing I want to note is, so this foreground model was fit to previous data set, which admittedly has, you know, the new data set has mostly the same data as the old data set. But actually, this BK14 foreground model was fit using the B-modes only. So the fact that it fits these E-mode measurements, you know, the fact that it predicts the right amount of foreground power, say at 353 gigahertz, or here at 220 pretty well, that's actually, you know, that's an interesting point about the fact that the foregrounds are compatible between E and B. With the one thing that I hadn't mentioned is that we're assuming an EE to BB ratio of the dust of 2. So this is something that Planck is measured, and that people are still, working on figuring out the exact explanation for. But it does in fact seem to be, empirically good. It seems to be an empirically correct parameter, at least in our field, is that if we take a foreground model that's fit using BB data, BB spectra, and double the dust power, it works well for the EMOs. That's of course only part of what we have here. We're most interested in the BB spectra. There's this dashed red line that's highly decorrelated. We'll come back to that in a little bit. So we can add in the BB spectra, which are now shown here in this bottom triangle. And then what you can see here is that the signal levels are much smaller. So if we look at, say, 95 gigahertz, where the foregrounds are the least significant, and we compare the lambda CDM EMODs, which are, order 1 micropace squared. Here for BB, if we look at the black line here, this is the lambda CDM lensing EMODs, and that's, you're down by 2 orders of magnitude in power here from EMODs to BMODs. And so what you can see is that even at 95 gigahertz, where you have the smallest dust foreground, that's a noticeable contribution here. As you go to high frequencies, you become increasingly dust dominated. And so, again, the fit here, the red fit, is based on the previous year's data. And what we see is that it's essentially still, quite a good description of our current data. Okay, so this was spectra that used 3 BICEP Keck frequencies. Oh, yeah, okay, sorry. Just to emphasize this point one more time, is because the red fit is using the previous year's data, it did not contain any 220 gigahertz, right? That was added in 2015. And so if you look across this row here, these are spectra that include BICEP Keck 220 gigahertz. And you can see that fit that was done using the previous year's data is still a good description when we added the 220 gigahertz data. So the idea here is that the model that we have is still holding up. The program model is still holding up as a good description of our data. So what we're going to do next is take not only those 3 BICEP Keck frequencies and this Planck high frequency map, but in fact we use those 3 BICEP Keck frequencies. We use 2 low frequency channels from WMAP and a total of 7 different Planck polarized channels ranging from 30 gigahertz at the low end up to 353 gigahertz at the high end. So putting that all together, you get 12 maps. Taking all of the auto and cross spectra from 12 maps, you get 78 spectra that are shown here. And if anybody has any detailed questions about a particular point, just raise it. Actually, we won't talk about that other than to say that again, you can look at all these spectra, you can plot this model on here, and you can do a while in terms of trying to understand what's going on. So rather than driving ourselves to distraction by that, we put this full set of spectra. We use this as the input to a likelihood analysis where the parameters of the likelihood are the cosmological parameter of interest, which is R, the tensor to scalar ratio, plus a whole bunch of foreground parameters that are our nuisance parameters, right? So this was the earliest version of it. This actually was not the BK14 result, but this was the joint analysis with Planck that used BICEP and Keck data through 2013. And so what we had done at that time was we had combined only 150 gigahertz data from BICEP Keck with all those Planck frequencies. Actually, that's not true. I guess it was only 220 gigahertz and 353 gigahertz from Planck. And what we were able to do is we were able to constrain a model that consisted of tensor to scalar ratio R. It had an amplitude of dust, and it also had this beta dust parameter. This is the frequency spectral index of dust, so how it's scaling with electromagnetic frequency. This parameter we had to put a fairly tight prior on, shown in blue. That prior is coming from long measurements over the full sky. And so what we did is we assumed that their measurements of dust over the full sky were representative of dust in our field. And able to produce this likelihood, which you can see there's a significant degeneracy here between R and the dust amplitude. But when you marginalize over that, you find that, oh yes, R peaks slightly above 0, but not in any sort of significant way. Dust, on the other hand, is detected with fairly high confidence. So we were able to update that with the 2014 data, and now what we have here is the most recent results from this last paper. So things have gotten a fair bit more complicated since that first plot. So what's happened is we've added an amplitude on a synchrotron component. So this is going to be a foreground component that gets brighter at low frequencies. We now have the frequency, the spectral index of both the dust and the synchrotron. Again, fairly prior dominated, so the priors are shown in these dashed blue lines. We also have these two panels here are going to be how those foregrounds, how the amplitude of those foregrounds vary with angular scale. So we're just assuming it's a power law. This is some power law slope there. And finally, a correlation parameter between the dust and the synchrotron. So this is how spatially correlated those two foreground signals are. They're both galactic signals, so you might expect some degree of spatial correlation. In fact, we have a possibly counterintuitive result of this black curve that they, a small preference for anti-correlated dust and synchrotron, yet not at all ruling out the zero correlation. Well, this is frankly just we don't measure it that well, right? Because as you can see, we don't really measure the synchrotron that well at all. Okay, and then the kind of the bottom line result is how well we measure the tensor to scalar ratio, and what you can see is going from the where seems to have run out. Okay, going from the gray curve to red to black is the constraint is getting tighter as we improve the data. It's also pushing down a little bit towards 0, which you can interpret as you like. And yet, of course, they're all in all variants of this result we're quite consistent with the tensor to scalar ratio at 0. Okay, so now I want to get back to in an earlier figure I'd shown this, these B-mode, selected B-mode results, and we included this dashed red line that was labeled as a highly decorrelated dust model. So this is a problem that started occupying us a lot in this most recent analysis, is the idea that we measure a dust signal, and yet in our analysis we're assuming that we can find these foreground signals by finding some contribution to the map that is scaling, its amplitude is scaling in frequency according to some SED, some sort of spectral energy distribution that is that's dust mode, right? And depending on how tight you want to be with your prior, that you could have some freedom in that spectral energy distribution, but nonetheless, we're assuming that there's some spatial pattern on the sky that's from dust. It scales in frequency, and yet its pattern remains the same. So the dust, in fact, could be something quite complicated. And so what we became worried about is, what if you have some dust signal, it does scale in frequency, and yet the pattern itself changes or decorrelates as you change in frequency. So decorrelates meaning that if you have a different spatial pattern at two different frequencies, when you try to cross-correlate them, you find that it does not quite line up. So this model with decorrelation is shown in the dashed red. And so the idea is that for the autospectra, which are down the diagonal, it doesn't make any difference, right? So we're still assuming that the overall dust power is scaling in frequency according to the particular SED law that we've assumed. But the only way you see the difference between the standard model and the decorrelated model is when you look at these cross spectra, and there you see that the dust is showing up at lower amplitude than what you might expect if that pattern is consistent across frequency. And so you can particularly see it when you have long lever arms in frequency, such as 95 gigahertz and 353 gigahertz here. And now if you look at those lines, it's a little bit hard to convince yourself whether or not this could be true, right? So you have something like, here at 150 gigahertz across 353, this curve maybe looks a bit low for some of these points, though clearly not in this first element. Yet here at 95 gigahertz across with Planck 353, what we see is that our data band powers, right, the points with the error bars, they're basically consistent with 0. We don't really see a cross correlation between 95 gigahertz and 353 gigahertz. It looks low compared to the solid red line. And so you might think that yes, we are seeing some decorrelation in action. This also showed up, I'm sorry, I don't know why this slide ended up being animated like this. So this also came up, we started this analysis all the way back in basically 2016. And around those times, Planck was also looking for this effect in their data. And they had, for instance, this paper, this Planck intermediate 50, where they looked for this and in fact said that they really thought that they saw this kind of decorrelation effect. So they were looking at the correlation between their 217 gigahertz and 353 gigahertz maps, both of which are dust dominated. And they were claiming that they saw significantly less correlation between those two maps than they would expect if they had a dust signal with a common spatial pattern. Then of course we took a really long time to do this analysis and write this paper, and so by this year Planck has worked on their data quite a bit more. They have their 2018 results release that's come out, and they've kind of walked back this claim about decorrelation. But in the meantime, it's of course something that we wanted to understand in our data. So what we did is, so we're still using this same parameterized likelihood method, but what we did was we added a new parameter, which we used the symbol delta. We didn't use anything quite as wordy as degree of dust decorrelation with spatial SED variation. But that's essentially what it is we have some model where the correlation between the dust signal at two different frequencies is going to depend, it's going to be proportional to this parameter, and it's also going to scale, sorry, that should be the log of the ratio, not the log of the products of the frequencies. Anyway, the idea is that you're going to become more decorrelated if you have a longer lever arm between your two frequencies. And we also just assumed some particular functional form with angular scale. So we're trying to do the smallest incremental complexity in our analysis, the smallest increase in complexity, and yet including this effect. So essentially what we did was we added this one parameter shown at the bottom right that says basically how much the signal is decorrelated. And in this case, it's normalized to the decorrelation between 217 gigahertz and 353 gigahertz, because that's what Planck did. Okay, so there's several curves here, and those have to do with choice of priors. So the green is sort of the loosest. So there we did not include any prior on this decorrelation parameter. And of course, you can see that it then has the broadest distribution in the bottom right hand plot. Whereas the blue and magenta are including 5% priors on the decorrelation parameter. The magenta one is we're actually assuming it's somewhat less than 1. The blue is that we have a prior that's centered at 0. You can see in all cases, our data do prefer some value that is somewhat less than 1. They do prefer some amount of decorrelation, and yet it's not, it's not particularly significant, right? It'd be very hard for us to say that we detected any such effect in our data. However, one thing that you do get is you'll notice in all of these cases, in all of these decorrelation models, it does shift the likelihood on R down. And essentially what's going on here is that both the, well, at least my intuitive understanding of what's going on here is in our data, we do see a tendency of, say, our 150 gigahertz map, which is our deepest and most sensitive map, tends to have a low cross correlation with the high frequency clock maps in particular. This is true for both our 150 gigahertz and our 95 gigahertz. They have a little bit lower than expected cross correlation with clock. Now this could, of course, be just noise, statistical artifact, and yet what the model is going to interpret it as is it's going to interpret it as some evidence, not strong evidence, but weak evidence for if you do not include decorrelation, it's going to see it as weak evidence that there is some of a steeper dust scaling law plus a CMB signal. So that would be some R greater than 0. If you turn on decorrelation, it says, oh, never mind that. I can now perfectly well fit this data with a decorrelated dust model, and I no longer need any sort of CMB signal in there. So that's the kind of squinting at a bunch of power spectrum plots and trying to make sense of these best fit models explanation for what's going on here. However, it turns out that this behavior where you add this parameter in and it pulls the likelihood of R down is actually fairly universal to this decorrelation parameter. And that's because what's going on here is you have a parameter that's bounded at one side, right? Having a decorrelation parameter greater than 1 is not physically meaningful. And so this is something that then, well, it caused a lot of debate and discussion about this analysis. Is basically, what do you do about a parameter where by including it in your analysis, if you include this in your analysis and you analyze, say, a simulation that does not include any decorrelation, you'll find that even without, it'll still tend to pull all of your constraints on R down in the negative direction. So with that in mind, we chose to present this as sort of an alternative analysis in the appendix of our paper and not the mainline result, given that A, we don't detect the decorrelation at any significant level, and B, by turning the parameter on, we do, in the absence of decorrelation, seem to bias our result down. That said, the cure for anything like this is to have much better data. So at some point in the future, not even necessarily the far future, hopefully we'll have much more sensitive data where if this effect is going on at a significant level, we'll see it in data. And then, really be able to account for it properly. Okay, we did kind of test this where, this is a validation where we're now allowing this kind of unphysical behavior of decorrelation values greater than 1. And in that case, we can uncover unbiased results. So this is not a bias in our analysis, but it's really a choice about bounding this parameter in the physical region. And that's the thinking fact that's okay, so now when we've done all this analysis and we're trying to understand inflation, so we can take those likelihood results, combine them with Planck, and what we get, well, this is from the previous result, and this is what we have now. And so what we find is first of all the Planck data, which for Planck alone or Planck plus baryon acoustic oscillations, you're seeing these parameter constraints that are in red. And so what you see the effect of the BICEP Keck data is to greatly improve this constraint on R, the tensor to scalar ratio. For constraining inflation, we also want to understand the scalar spectral index, NSFS. That is not particularly coming from our experiment at all. That's all from pump data. But what you can see is it is, having this additional BICEP data, constraining tensor to scalar ratio, really contracts things a lot in this vertical direction, and you start to, for instance, strongly rule out some of the inflation models. Here we've marked just the phi squared and phi models. You can, of course, make these plots with a large number of other models, which, for instance, if you look at the long paper, you will you'll find some very nice versions of that. But the point here is that that things are getting quite a bit more constrained. Sorry, most recent analysis is not less than 0.07, it's 0.06, though it's, as you can see, kind of incremental progress. So now, just since I'm just about running out of time, talk about things going forward. So where we are now is through this point here, BICEP Keck 2015, and this is now forecasts of the observing program going forward into the future. And the key point I want to make here is that really the very exciting stuff is around the corner. So the analysis that we're working on now will not just be a BK16 analysis, but we're given how far we've slipped back in time, we're ready to try to catch up and add 3 more years of data into the upcoming analysis. And not only is that 3 more years of Keck data, but we now have BICEP 3 online, as you can see from the top right of that image, which is a lot of sensitivity at 95 gigahertz. We'll also have much more 220 gigahertz data from Keck. There's the 270 gigahertz data from Keck, which will take a bit more work to make sure that we have what we think we have there. But this, this step from BICEP Keck 14 to BK15 was a bit of, like I said, an incremental step forward. And I just want to make the point that this is going to be a much larger step forward, something like a factor of 2 in terms of our sensitivity to harm. And that's, based on what we think are very accurate projections, from a lot of prior experience. So then in the upper right, you can see, starting in 2020, BICEP array coming online. First coming online at the low frequency, those two shades of red are meant to be 30 and 40 gigahertz low frequency receiver, and 150 gigahertz in green. So that's not far away from happening. And so I just wanted to show you that not only do we have renderings, of course, of what BICEP array is going to look like, this cutaway rendering showing 3 out of 4 telescopes, but we actually have a BICEP array mount. So this is in the high bay at University of Minnesota. This is a pretty large object, as you can see from Colin sitting there in the foreground. And so it's really coming together. I'm starting to get built. There's cryostats. There's starting to be detectors as well. And so this is going to be really exciting next year. And then the last thing I had is, in fact, this mount not only standing up in the high bay, but we can actually make this move. So this is, of course, quite recent, taken by some of the grad students at University of Minnesota. So a lot of work to do in the next year, but we're really excited about this going forward. Keep these results coming along. So that's it. Just got a nice photo. Another former KICP grad student here, Keep Fairland, that somebody is learning over. But that is then the end of my talk. So any questions?
Thanks, Colin. We have time for some questions. Is there any in the audience?
goes first, I think, between.
Oh. Hey Colin, on the dusty correlation stuff, couldn't you fix the having to put a prior on this decorrelation parameter by just using a more physical dust model? I mean, decorrelation just means you have multiple components, and you're picking one up more at 150 than you, and the other one more at 350. So have you tried that?
Yeah. So the natural thing would be to have have that beta dust SED parameter have some spatial fluctuations, right? So that the scaling of dust with frequency is different in different parts of the field than others. So that's actually where ultimately this frequency scaling, which again I botched when I was typing up on my slide, came from is this kind of logarithm ratio of the frequencies. Was ultimately inspired by a model, and this is, if you look in the appendix of this Van Single et al. Paper, so not a BICEP Keck paper, but somebody working with Francois Hollande. So that model is ultimately inspired by this idea of varying spectral index. We have also, I did at one point play around with a kind of two-component dust model where you're just mixing those two components of the frequencies, and so you can do something like that as well. So ultimately, we wanted to squeeze this into our likelihood analysis. So what that requires is some prescription for how it affects the auto and the cross spectra, and that's where we end up modeling it in this way. But yeah, I think it's an interesting question how physical models in the map onto this sort of likelihood analysis. I didn't show the plot here, but we have what we did. Well, sorry, not a plot, but we have a table in the paper where we took maps of physical dust models that are done by various people outside of our collaboration, and these are the same ones that we've been using for the CMBS4 simulations, and have run them through this analysis. Those models, even the ones with varying spectral index, tend to produce very small levels of this decorrelation parameter, indistinguishable from one. I think it's still, well, we haven't fully explored this, but I think it's still an interesting question how you map from those models in map space to what we're talking about in terms of the power spectrum, and what's the right way to describe it or parameterize it. And one of the problems there is clearly we don't have the signal to noise to see this. There's not a lot of guidance from the data right now. So hopefully that answers.
Could you go back a couple slides to the matrix of E-mode measurements? And yeah, that's good. That point at L of 180, that last point.
For the 150 gigahertz levels?
Well, for a lot of them, yeah. Is okay.
Yeah. Right. Yeah, so it's...
Oh, is it all driven by the 150? It looks low.
No, it shows up in 95 too, right? So one thing is that, in some ways it's reassuring to me that it shows up in 95 as well as 150, because really those are not independent measurements. For the E-modes, we're pretty signal dominated. And so...
what is it?
Yeah, so it's low. It's not dramatically low. So if you do the chi-squared of this model to the data, it's fine overall. So yeah, it certainly is a low point. It also helps that we're zoomed in on just the first 5 band powers rather than the 9 that we include in our analysis. But the chi-squared on this is it's not anything that's particularly worrisome. So
Are you worried that the lower L points are too good a fit?
Well, right, maybe that's why the chi-squared works out. Now, I guess personally, I'm not worried about it. So that, so this is a, at least at 95 gigahertz and 150 gigahertz, this is definitely a very signal-dominated measurement. So those two autospectra are not, they're not at all independent measurements, and you do, see again that the second points are both a little high. The fifth points, as you point out, are definitely noticeably low. And so, just focusing on what are the other, then the question is it outside the range of statistical explanation? And I'd say no.
All right, we have time for another question or two. Back.
Okay, can you go like a slide up,
Uh,
like with the street plot? Yeah,
this
that's,
one. Yep.
so this is, am I expecting to have like a 2 times more sensitivity in R, based on your projection plot from BK15?
So, you mean going to the BK18 in the future?
No, just like going from BK to BK15.
Okay, yeah, so you're saying going from,
It's okay, like my real question is, the reason that it's not shrinking that much, is it because your current program model is more complicated, you're marginalizing more things, or your analysis choice changed otherwise? Is that shown?
so if you go back, so again, when we're looking at that forecasting plot, and in particular looking at these past results on that forecasting plot, the sigma R that's shown there, progressing downward with time, is in fact the sigma R that is for the marginalized constraint here. There's maybe a small additional complication that really it's a sigma R that we measure off of the variation in the peak position off an ensemble of sims. The fact that these peak slightly above 0 makes them extended a little bit more, but that's really not a significant difference. So what I would say is that actually the width of these distributions is in the upper left here is consistent with the points on that plot, and getting, like you said, roughly a factor of 2 better.
And like the modeling and analysis choices are the same between the grade.
The model, well, the model choices here, they do vary a little bit, and the model choices, the model choices in the projection plot are consistently this full model versus this earlier analysis that was a partial model. Yeah, I think all of those are things kind of at the 10% level. But
They're not nothing.
Yeah. So it's if you really started comparing numbers, but in terms of looking off the plot, they're not going to make a big difference there. So more or less, the sigma R values that you get are essentially the width of these distributions.
Thanks.
All right, I think in the interest of time, we'll cut it off there, but you're welcome to ask questions individually later on. Thank the speaker once again. So, as is our tradition, we welcome students